Good morning. Today, in contrast to my yesterday's talk, I'm going to be more theoretical instead of being less practical. So this time we are going to learn some fundamentals of linear optical quantum computing. So let's first of all try to explain what this combination of four words mean. Okay, because if you are familiar with linear optics and quantum optics, you immediately realize that bringing these two together is not immediately meaningful. Okay? Because first of all, this linear optics is all about basically superpositions of linear solutions of Maxwell's equations, right? So we know that in linear optics, basically, we have non-interacting and uncorrelated independent electric fields in superposition at best. But in quantum computing, as you have seen in the previous lecture, it is all about putting qubits together in highly correlated states. Okay? So these two seem contradictory. So let's put this in a more formal context. If we start with Maxwell's equations, then we know that if we use constitutive relations for the free space, where the vacuum permittivity and permeability are just constants, you can convert these four equations to two independent wave equations, or even actually one equation in terms of the vector potential at the end. Okay? And this equation is a linear equation, which means if you have two solutions, they are linearly independent, you can superpose them and still get another solution. If you take absolute square of that for the Poynting vector or intensity, then you can get some kind of correlation between E1 and E2, but this is only an interference, a classical interference. Okay? Which is not what we need to do quantum calculations. So this is all about linear optics. If you want to go to quantum case, what you do is you quantize this electric field. Okay? So this expression you probably have seen in Jacob's lecture on introductory quantum optics. You replace the amplitudes of the electric fields with some operators. So this A and A figure are creation and annihilation operators of the photons with wave number K and polarization E. Okay? So this mu is three different polarizations of the photon, and K is the direction of the photon propagation, and its magnitude is related to the wavelength of the photon. Okay? So after this quantization, you can realize that these photons of different modes in different directions, different polarizations, different wave numbers, and all these degrees of freedom are quantum mechanically uncorrelated. On the other hand, as you have heard, polarization, frequency, or energy, or even direction, are degrees of freedom where we encode our photonic qubits. So immediately linear optics tells you that you have no chance to quantum correlate photonic qubits. Okay? So the lecture is over. You can go enjoy lunch or whatever. Yes, there is no linear optical quantum computing. Okay? Well, unfortunately there is, because this is the big surprise. Yes, I want you to motivate yourself that expect there is a surprise. Even if everything is linear, there is a way to quantum correlate photons. Okay? So you expect there should be some ingenious people around that come up with a brilliant idea that allows us to do this. Okay? So wait, and you will see. All right. So why do we expect photons to be good qubits? So first of all, let's assume if you wait, you will see that we can correlate quantum mechanically qubits even within the linear regime of optics, even if they do not interact. And then this non-interaction becomes a good thing, okay? Because in the spontaneous emission of the superconducting qubits, it was our enemy. Environment is enemy of superconducting qubits, because superconducting qubit easily interact with the vacuum fluctuation. But in the case of photons, environment is just a bunch of another set of photons, and photons just don't care each other. They will not interact with the environment. Yeah. So if you want a room temperature quantum computer, then go photonics. Okay, so this is good. And photons, they fly around. It is very difficult to trap them. They are very fast, and these are good things also for computation. You can make distributed computation easily. Well, this is somewhat bad because they are so agile and fast. You can easily lose them, but it's a technical issue. You can mitigate this error. Okay. Well, at the end of the day, if you visit some laboratories here, I think you have done this, or maybe you will do, but you will see lots of optical equipments on so-called optical tables. Okay. So this is mess. Yeah. So this looks like, suppose, some computation object. So scalability means you need a larger optical table, maybe larger room, or maybe rooms, and some types of optical elements. Alignment of them is also very big trouble. So scalability can be a problem because we want our quantum computers are so small. Yeah? All right. So, but these are again technical problems. Fundamentally, photons are good qubits. Their most important problem is solved, that they are not caring much about the environment. And there is one challenge of that on demand, they should care, at least with some photons they interact, they should be able to do that. But wait, and you will see this is possible. And it is a big surprise that comes to physics, that in a linear system we have interaction. Okay. So if the photons are good qubits, what kind of information you want to encode on them? In the quantization, you can see several options. The degrees of freedom in the wave number is the direction, the magnitude of the wave number, which is wavelength or energy or frequency, and polarization. So these 3 degrees of freedom, and also I didn't show it, but there is also some time dependence. The time, these 4 degrees of freedom, basically space and time, they're all available for us to encode the qubits. But some of them you can realize that, like this distance energy, are different than polarization. I can count the polarization 1, 2, 3, but I cannot count the energy. Yeah. So we make a distinction that it is possible to do either discrete or continuous variable encoding. Then this immediately separates the industry also fundamentally. So there is one set of industry that hopes that continuous variable encoding will be the winner. And based on this, like Xanadu, they prefer continuous variable encoding using the quantum coherent and squeezing effects. And companies like PsiQuantum, they prefer to use discrete variables like polarization, some certain frequency paths, and direction. And also timing, yeah? Some countable degrees of freedom. Well, both of them are very well funded, especially PsiQuantum is one of the richest, probably funded companies. So hopefully they will get some interesting results soon. All right, so let's look at polarization as our first choice, because this is very common, and what we have discussed with the QSKIT in terms of qubits with 2 degrees of freedom, polarization is the closest one to binary qubits in superconducting also computers. So this is one kind of more universal set of ideas you can find using the polarization degrees of freedom. So let's write a single mode, single color, single frequency electric field. with horizontal and vertical possible polarization. And these are just amplitudes, relative weights of different polarization components. So we choose horizontal direction as the x direction, and y is the vertical direction, and z is the propagation direction. And you can have also phases, but this phase and this amplitude can be combined with the earlier identity so that you can use complex representation. Also in quantum optics, it is important to use complex representation. And here you can have everything written in exponentials of spatial and time degrees of freedom, and some phase which is absorbed, which can be absorbed to amplitude. Okay? Then you can drop this reminder that you have to take the real value for physical reason, and just use this complex expression. This complex expression can be used similar to what you have learned in quantum optics in the sense of second quantization of the electric field, but I have a single mode and I will only focus on the polarization state and hide all the other degrees of freedom, space and time, they are hidden. So in this case, I can make a shorthand expression, keep only the amplitudes, forget about the space, I can even drop the time, just focus on this amplitude h and amplitude v states, and this looks like a qubit. So if you replace h by 0, v by 1, this will give you Qiskit notation that we have learned in the previous lecture. And you normalize it, yeah? Okay, and how do we know that they make good qubits? You can optically test that they are orthogonal. You cannot interfere horizontal and vertical components. This also makes sense from classical optics. It is translated to quantum mechanics as the inner product, that it is 0. And inner product of the same basis, horizontal and vertical, is 1. This basis is called canonical basis or canonical polarization basis. Canonical in science usually means standard. Okay, so this is the standard application. You can use matrix representation, again, similar to programming for Qiskit, for instance, or penny lane, whatever. You can use matrix representations for H and V, then make linear combination of superposition states. So what is important for us here, that horizontal and vertical, which is the standard choice or canonical choice, is not unique choice. Your device may prefer to work with, for instance, circular polarizations, right, and left circular polarizations, and all these different polarizations can be mapped back to horizontal and vertical basis as well. So you get basis transformation, but you don't have to work within the canonical region. Well, how to generate this set of bases uniquely? If you only need horizontal polarized photon, you can remove the vertical polarization component from the full electric field by passing it through a polarizing beam splitter. So polarizing beam splitter allows splitting of electric field depending on polarization. So if it is horizontal polarization, it will transmit, but it comes with vertical polarization, it will be reflected. Okay? So if you do this with the classical field, you can see different amount of light passing through, depending on reflectivity, transmission, properties, coefficients of this polarizing beam splitter. Okay? It's basically some transparent prism glued to each other, two prisms glued to each other. Well, but can we do this with photon really? Because by definition, photon is the quantum of light, and quantum of light means indivisible. Yeah, so it is indivisible energy packet of the light. So there is a difference between sending a classical signal and quantum signal to the simplest beam splitter. A classical signal can be found at the both arms simultaneously, but a quantum signal or quantum photon can either be found here or here. Okay? It cannot be found in two. You cannot split a photon. And this allows us to do quantum operations even with a simple beam splitter. But here we should realize an immediate difference between a superconducting gate and if we want to imagine a beam splitter as a quantum gate, because this works non-deterministically. So we will find our photon sometimes here and sometimes here, okay? But in Qiskit, the gates do not work like that. So photonic elements can be envisioned like quantum gates, similar to AND gate, OR gate, etc., and logic gates. But you should always remember, since photon is indivisible, they are probabilistic gates. So our linear optic quantum computation fundamentally differs from other gate-based implementations. So if the gate or beam splitter works probabilistically, what you can do is you can make statistical sampling to get closer to classically expected result. You can send an ensemble of photons to define probabilities, okay, and try to get more and more closer to classical expected result. And here probability, according to quantum measurement postulate or von Neumann measurement theory, is simply if you know the state, you make a projection measurement, and the amplitude square is the probability to get this particular outcome after the experiment. And at the end of the measurement, you destroy the state, original state, and you project out the outcome to the one basis state, which is the measurement basis. Okay? So you choose a measurement basis, make a projection measurement, and at the end, you find one of your base elements at the output, depending on some probability. This collapse of the wave function is usually a problem, but in the case of optics, this can turn out to be an advantage, and the latest breakthroughs in the linear optic quantum computing is actually taking advantage of the controlled collapse of the wave function, which is known as measurement-based quantum computing. Okay, so in general, what are the overview of a linear optical computing device? Okay, so you need a reliable source of photons, ideally single photon or entangled photon generator, okay? And it should ideally work deterministically on demand. Then you will send these photons, ideally large, many of them, to some on-purpose designed optical device circuit. And the modern devices are using some on-chip implementations. And then you measure the output and make some post-processing. And this very looks similar to what we have defined as the 4 steps of quantum programming. Okay, so these are programmable chips, basically. So I will only shortly introduce a little bit of basic concepts of this single photon source and single photon detectors. And I will focus mostly on circuit elements here, because you will have a chance in the school to see and discuss these experimentally in more detail than what I can tell you. Okay, so to generate single photons, what you can have is you have 2 options. One is to use spontaneous chromatic tone conversion, which basically use some nonlinear crystal. Okay? Nonlinear crystal means the dielectric and electric constitutive relations have this permittivity, which also changes with the electric field strength. And if you have large electric fields, you have stronger nonlinear response. And you can generate multiple photons, ideally 2 photons, which is a photon pair. And in this case, they are interacting because it's no longer vacuum, it's a nonlinear optics. Yeah? Well, using nonlinear crystal in a linear optical setting, you can say we are cheating. Let's make everything linear. Yeah? Well, you can do this if you use single photon emitters, like what you have heard last evening from Özgür about hexagonal nitrate and or NV centers or quantum dots, like single emitters. And they are also very popular because they are more deterministic in this case, because if you have a photon pair, if you only need one of them, you have to collapse the wave function to one of them. And therefore, as we have discussed in the von Neumann postulate of quantum measurement, this makes everything probabilistic. Yeah? So this is a deterministic source, but you can have more deterministic source on demand. Now, suppose we have this single photon source, how to detect the photons? Well, the state of the art suggests that we should go superconductors. So we need cooling, and cryo is expensive. So this is an expensive component of the let's say photonic linear optic applications. So how it works is it's a good idea. You let the current circulate on a superconductor, and you on purpose change the superconductive property locally by heating it somewhere, make a superconducting phase transition, make it not superconductor, so that you can change the current voltage characteristics here, and you can take this change, significant change, to detect even a very tiny energy, like a single photon. Yeah. Single photon is very, very tiny energy. Okay, so these are enough for us for the fundamentals of how these devices work. And for the photon detection, now we have very, very high efficiencies, like 90%. So why we talk about this efficiency? Because in this case, you may have some dark counts, and also you may have some errors due to that reflection of the photon without click. So you have loss of efficiency, loss of detection reliability. But these are technical issues, and currently even 90% is improved. You can have close to 99% efficiency. Okay. But the more better, the more you need to pay usually. So this is expensive part of the object of the device. Okay, so let's focus on the center between source and the detectors. Okay? So the simplest circuit can contain the simplest element, which is the polarizing beam splitter. Okay? So what will it do? So last time we have seen that if it is horizontally polarized, it will just transmit. If it is vertical, it will just reflect. Yeah? So if you have an unknown state, you can make a discrimination circuit. And you can run this circuit to decide whether this is in horizontal and vertical state. Yeah? Because since this is a single photon state, even if it is not in H or V, but some combination or superposition, it's still a single photon state. It's a single photon qubit. And you can distinguish whether it is horizontal or vertical. So this is very trivial. Now let me give you a homework, because you can see this table here. There are state transformations where diagonal polarization or circular polarization can be written in canonical basis also. Yeah? So you can use this state transformation to design a little bit more complicated circuit to discriminate whether this incoming state is in circular or diagonal basis. Yeah? So this is my question to you. Well, this can be done. Let me give you some answer here. Basically, you can simply rotate the beam splitter by 45 degrees using the rotation operation on vectors. Yeah. Then you can simply do the math here to show that this will work if you just rotate the PBS 45 degrees. But this rotation of polarizing beam splitter is not the best choice. Yeah? Can we do something better? Because you see all these discriminators just change the direction of the incoming light. In our circuits, we don't want this too many directional changes. And there is a very nice device that without necessarily changing the direction of the incoming light, you can still make operations on the polarization changes, which is known as waveplate. Okay? And waveplate is a very simple object. It is just a stone. Okay? Just a very special stone. It is a calcite, yeah, or quartz. You can see some photo here. Okay? So we can distinguish this calcite by having some birefringent property. Okay? So you can see double. Yeah, it is a stone which is drunk. You just see double. Yeah, so you can distinguish this effect by saying that when light passes through it, there are two axes. One is ordinary or optical, relative to optical axis. The other one is extraordinary. But there is a speed difference depending on direction. Okay? And because of this speed difference, the signal just delays relatively, and you can see double. And this delay can be used on advantage to design different rotations on polarization state. Okay. So here, this is a backlight, basically a calcite, okay? And its purpose for us is to make a rotation operation on polarization state. And you can see some math here. This is the refractive index, which is changing the speed of light from the vacuum speed. Then you can use definition of speed by distance over time, lambda over period, wavelength over period, and go through the math, also define the use and take advantage, exploit the definitions of wave number and frequency or distortion in vacuum. And just go through this. And the refractive index is also then given by a change of the wave number, or k to k0. So if you substitute this k to k0 to the complex representation of the electric field, and just factor a global phase, overall phase, which is not important, you will see that one component relative to extraordinary and ordinary axis has a phase shift, okay, as it transmits through the calcite or quartz. And from here you can see this phase shift is depending on the different refractive indices in homogeneous refractive index, in anisotropic refractive index, depending on the length of the crystal and the vacuum wavelength. And therefore we can tune this on certain numbers. If I tune the phase shift to simply half wavelength, I call this as half wave plate. And half wave plate, if you just put the numbers here and choose some length of the calcite or quartz, okay, and make sure that the phase shift is always pi, you can find the effect of this calcite or quartz crystal on the incoming light. So this is a transformation matrix on the canonical, horizontal, and vertical polarization phases, the action of a half-wave plate, okay, which looks like somewhat similar to Z operator. Yeah? If you just change the order here, or change the order of the phases, you will see this is actually a Pauli Z gate. Yeah? So half-wave plate acts like a Pauli gate, actually. And you can just see that this is acting like the Z gate. And here you can do a little bit more, you can be a little bit more general. So you can choose horizontal axis and some angle between the horizontal and the optical axis as alpha. And you can show that half-wave plate can be written in more general sense. So basically, if you rotate the optical axis, you can generate a continuous set of different transformation matrices. And half-wave plate for particular alpha for the Z gate is a special case, and this is more general. So I can generate different quantum gates using the different orientations of the optical axis. Quarter wave plate, I don't want to explain how it works, but it is a little bit more general, and this is its transformation matrix. So you can only work maybe this part as your homework and try to find this from the literature. But for completeness, this is written here because it has different purposes for, especially in non-canonical phased rotations. This is somewhat preferred. So this is some example how we can make polarization bases. We have already seen that this is for canonical polarization based measurements. And if you put a half-wave plate just in front of the polarizing beam splitter, you can also work out that this will just measure states in this time in diagonal basis. Okay? So basically, you write the matrix of these optical elements, and you will immediately see the signal. And this is for the circular polarization. So why I added these three here? Because combination of these three are very important in what is so-called quantum state tomography, as we shall see. By making these three measurements in all three different canonical, diagonal, and circular bases, it is possible to uniquely characterize a density matrix of the photonic qubit. All right, so the purpose here to define this intermediate circuit between the source and the detector, we just need to be able to put some photonic quantum gates and make some combinations of them to run quantum algorithms. Okay. So we need to find photonic analogs of them. And remember, in my mind, there is always this particular issue that they will be probabilistic. So my device will work on the odd days of the week and may just retire on the even days of the week. So I don't know, it will work sometimes, it will not work sometimes. But we can mitigate this also. Okay, so we are looking for this quantum gates for horizontal and vertical as economical basis. So we change our 0 and 1. Remember in our acoustic, we were using 0 and 1, but in photons we have HV-BH combination. Okay? So on paper as a theoretician, I am done. I have written Pauli operators in canonical basis. I can go home and give this paper to my experimentalist friend. Just ask him that or her that do this. Yes, how she or she will do this. Well, at least I gave this matrix, right? So these guys, experimentalists, know how to orient optical axis relative to horizontal axis. So if you choose a special alpha, you can see we can generate the photonic Z gate easily. Okay. So for the other gates, for instance, if you choose orientation 3.4, 135 degrees, then you can get Pauli X gate. Yeah. So you have this calcite crystal, a stone. You have a stone, you rotate the stone, and you get a Pauli gate. It's amazing. And for the Y gate, it's not that trivial because it's complex. Yeah, Y gate has this I. So what you need is you should bring this I there. So I means actually basically in optics, this I means a phase shift. Yeah, so you need a phase shift. So you first swap. This is a swap gate similar to X gate. But in addition to swap, you put in particular phase to complete the Y gate operation. So you need two stones. Okay, two stones to kill one bird to make a Pauli Y gate. So another important gate in what we have seen in the last lecture to generate the entangled state before the control NOT gate in Özgür, we always introduce Hadamard gates. Also in the Grover algorithm, we introduce 2 Hadamard gates. Also in the Oracle, we introduce 4 Hadamard gates when we want to amplify the probability. Okay, so we need lots of Hadamard gates. What's the Hadamard gate? It is named after Jack Hadamard, actually. He's not a physicist, he's a mathematician. And he introduced this Hadamard transform to study Fourier transform. Okay? So Grover algorithm was very good. It allows for quadratic speedup. Yes, it was a quantum advantage demonstration. But the quantum Fourier transform is even better. It is another algorithm with quantum advantage. Yeah? And Hadamard gate plays a role in all of these guys. And this is the simplest Hadamard transformation that we can do. And to do this in photonic case, we convert the computational basis to canonical basis, H and V, and write the Hadamard gate in canonical representation. Okay. And you can, of course, do this exercise. You can do it by mind. You don't need pen and paper. Just if you add this to this horizontal state, you will get this basically H and V superposition. And this is important that we have quantum superposition. Okay. And the nice thing with photonic qubit, that kind of transpositions and that kind of quantum coherence or quantum superposition is very long-lived. Because this is not interacting with the environment, even in room temperature, you can have this Hadamard gate, yeah, if you can do it. So how we can do this in experiment? Again, we choose a specific angle only. Okay, so we have the stone, we rotate it by 5 pi over 8, 112.5 degrees, and you get a Hadamard gate. So we can make a quantum circuit here. It's room temperature. As a homework, every Friday you can bring calcite crystals, quartz crystals. Two of you will be Hadamard gates. Yes, rotate them. You can make a sequence. I will send you a laser. So it's very easy to make a quantum computer. All right. So by combining all these stones or quantum gates, we can even characterize an unknown state perfectly by quantum state tomography. Okay. So what you do is in quantum state tomography, you generate lots of photons as an ensemble, very large number, like 10,000, for example. Then you send them to polarizing beam splitter with some half-wave plates combinations. These three measurements I have told you for canonical, diagonal, and circular polarization measurements. Each single shot will give you a probabilistic result. But if you repeat this over an ensemble, you will collect a result to characterize uniquely your unknown symmetrics or unknown state. How it works? Why do you need lots of polarization measurements? So this is my unknown state. Okay. How many unknowns do I have? I have two real amplitudes and one relative phase. Global phase is not important. So I have three unknowns. Okay. So if I only measure or discriminate H and V using a single polarizing beam splitter, I will have one unknown left. Okay. That's why I go to the other polarization bases like diagonal and circular. Okay. So in the diagonal case, you have one more equation. And in the circular case, you have one more equation from measurements. So you have three equations for three unknowns, okay, for three different bases, canonical, diagonal, and circular, three bases for three unknowns. This is the heart of the quantum state tomography. Okay, so now we have all the tools. We have single photon source, we have set of photon detectors, polarizing beam splitters. So in between, circuit do something and give us output, and we can find this output by quantum state tomography. And let's look at other alternatives. So far, we have discussed only the horizontal and vertical, diagonal and circular polarization bases to encode quantum information to my photonic qubit. But if you look at literature of linear quantum photonics and computations, you will see alternatives. Okay? So for instance, this arrival time in qubits, quantum communication people love them a lot. Also radar people that they are trying to do some quantum radars, yes, or sonars, they also look at this a lot. So this is arrival time difference, which is probabilistic. When an emitted photon from a source comes, this only comes in probabilistic times. So you can have some time delay between emission, and then you can use this time delay to encode information. Okay. And the same thing can be done in the energy also. Well, you can say that I have different options for discrete variable encoding, but these options sometimes can be converted to each other. And here, two important concepts in this linear optical quantum computing is multiplexing and demultiplication. Demultiplexer. Yes. So this basically gets a signal, okay, which is, for example, from quantum dot, it emits some pulse sequence, some photon pulses. Yes. Then you can introduce here some delays. Basically, delay means that photon is of course very fast, but you can introduce some short delays on them by rolling your fiber or making it going through a longer distance, so you can generate different delay times. Okay, so therefore you can generate different, you can map different time delays to different space encoding. So these are convertible. Okay, so another possibility. So we have seen we have polarization, discrete variable, time discrete variable, frequency discrete variable, and they are convertible. And also another possibility is to use discrete variable, which is direction of propagation. So in this case, for qubit, I need two different directional propagation, horizontal and vertical. And horizontal is denoted by x, vertical is denoted by y. And horizontal here is chosen as 0, vertical is chosen as 1. Okay. And to make a qubit, you should be able to controllably produce superposition states. And this is an interferometer. You split the paths, combine them again on them. These are beam splitters. Okay. So here this goes through this beam splitter. This goes through beam splitter. Okay. But whenever direction changes, x changes to y. And you can produce some phase shift also. And you can see a simple mirror instead of our quartz or other crystals, calcite, etc., biacritic crystals. You can simply use a mirror here or bend the fiber, basically, if you like. If it's a fiber, not a free space, you can have a fiber also. If you bend it, you can make a mirror. So basically, this acts like a bit flip operator. It's like an X operator. And this acts like a Z operator. How to make Z operator? For instance, I can just light a 5, make it longer, and then I make a phase shift. Yeah. So it is, there are different methods. But basically you can generate by controllably different amplitudes, different weight factors, and phase shifts make it complex and make a qubit easily using directions. So these are all options for different applications. Well, this is also another possibility. Here, this is so-called path qubits. This time we take two resources or two paths. One is two different waveguides, basically. And I have a photon here, let's say. In this case, this is called, if there's a photon here, this is, let's say, this is A, so this is special mode A. And there is one photon here. If there is one photon in this special mode B, it is one photon here. But even if they are empty, we just, in quantum optics, we have to remember this is, there is still something there, which is vacuum. Yeah? It can fluctuate, so it is a real object. So we also need to be aware that we should write a vacuum state always. If something is empty, again, you assign a state there. So therefore, this is not a true qubit or a genuine qubit. We say this is a logical qubit because it is actually a combination of a two-qubit object as if it's a single qubit. Yeah? So it's a logical qubit. So you can use the creation operator to denote it in a shorthand notation. If the creation operator for the path B acts on vacuum, this is a two-photon vacuum, it generates this logical 1 state. If it acts on the A mode, then it will generate logical 0 state. And these are called some dual rail qubits. And they are very popular in programmable circuits of photonic systems. Why? Because everything is very easy. As I said, instead of these calcite crystals and so on, you can simply use a fiber, bend it, make a, and here I need a beam splitter. And instead of again a different object, you just tear your single fiber in two parts and you can immediately get a beam splitter. So you can use waveguides to make a nice circuit. Yeah? And introduce a phase shift by simply change the width of this or length of this, introduce phase shift or introduce different rates and easily create superpositions. Okay. Well, here, let's come back to our original motivation. Okay. I told you that in Maxwell's equations and wave equation, you have linearly independent solutions. Even the classical interference is incapable to generate quantum correlations and entanglements. So you need some ingenious idea how to entangle photons using only linear optical elements. So the ideas come from these three persons, KLM in short, Milburn in 2005. It's a nice article with very detailed explanations. It's a long, it's a lot of ideas. Okay? But let's focus on the basic idea, how we can correlate photons using the optical elements. So this is one example, which is making a Z correlation or controlled Z operation using only linear optical elements. Okay? So we send the light here, to this upper beam splitter, and there is another channel here. Okay? So if this photon is found with some probability at the upper channel, then it is lost. It is not our concern. We want to make a 2-qubit gate, and there are too many outputs. So some of them are lost to us. Okay? We just repeat the experiment. So we have an ensemble of photons on the left-hand side. So only we care about these 4 detectors and 2 channels, okay, to represent a 2-qubit operation. Okay. So the idea of this KLM group is that, okay, I cannot really make an effective or direct interaction between the photons, but probabilistically I can generate my desired states at the output of a linear optical evolution. Okay. So probabilistically, this is exactly working like some control Z gate. Yes, it was a gate we have used in the oracle of the Grover algorithm. It's a very important gate. So we can do this, but only every 1 operation out of 9 experiments. Okay, so for 8 times it will not work, but 1 time it will work. So the most interesting idea of the KLM scheme is that this is not enough. Let's make a cascade of them. Remember the GHZ state circuit I drew for the generation of n-qubit generalization of the belt state in QSIP? There is a cascade of control NOT gates. Yes. So the same idea here, like a probability amplification of the Grover search, you have here a cascade of this setup and like a very huge number, right? Like 1,000 or 10,000. Yeah, it is. Of course, once the paper appeared, some people said, okay, this has too many resources, yeah, too many photons, too many gates. But with some technical improvements, now it is getting clear. So you cannot do this on optical tables, right? But if there is a way to put all these optical tables and shrink on a chip, then you can do this. That's why these getting more popular, because nowadays you can put everything on a chip. So this you can easily just run matrix elements of beam splitters and run this input, and you will see that you can actually, it's a good exercise, just try to get this number. And the cascade is of course complicated, you can read the paper. Then another important gate, because we have seen Hadamard gate is easy, but after the Hadamard gate, if you apply control NOT gate, you have entangled photons. Okay. So this time the circuit changes a little bit. Again, you have beam splitters, but it is different than this setup. Yeah, you have a different setup. You can look at this paper, how this setup is calculated. There's a general scheme from the classical optics in scattering matrix elements and transfer matrix of different beam splitters, mirrors, etc. From transfer matrix in classical optics, you can predict the shape of these circuits and gates. So there's a general scheme here in this paper. You can find this also in this paper. Again, this is probabilistic, but you can make a cascade of this using the KLM idea to produce an almost deterministic, asymptotically deterministic control NOT gate for linear optical case also. Okay. So you can effectively generate entanglement or effectively simulate nonlinear result of nonlinear optics by using linear optical elements in large number asymptotically. Then you get effective nonlinear. Okay. So as I said, now we have some set of calcites, quartz, and very large system. So this can be, even this setup can be done by quartz crystals, yeah. So you can use crystals again, but you need a collaboration of 10,000 people to get maybe this state, yeah. So this is a very large computer. So we call this as the Stone Age of linear optical quantum optic photonic computer. Okay. So the main purpose is actually how we can fit this on a reasonable size. Okay. So here the waveguides come to the rescue. So most of these optical elements, beam splitters, mirrors can be easily simulated by orientation changes of the optical fibers and waveguides. For instance, if you bring tapered fibers close to each other, you can make some directional coupler or beam splitting type of effect. You can bring them closer on a chip and build this on a very tiny scale and make a very tiny, very compact Mach standard interferometer. Basically, these are heating. It's by heating controllably, you can elongate the length a little bit and create some phase shifts. You can have two beam splitters and phase shifters to generate a Mach standard interferometer. Okay? So these are just thermally introducing some phase shifts. Okay? So by encoding the qubit to not polarization, not direction, but mostly to paths, we can have a very compact on-chip designs, which is called photonic integrated circuit. Okay? So from Stone Age to the future, this is the way to go, at least the current state of the art. And another issue is optics allows us to look at the problem a little bit different than this, what we have learned in QST or superconducting circuits or the circuit-based approaches or gate-based approaches. What we can do is we can generate large number of photons and we can generate very large, robust quantum entangled set of photons because they will not interact with the environment. They are more probable. Remember our decaying pessimistic curve of n-qubit JC state on the real superconducting computer. After 10 qubits, you lose entanglement in a real quantum computer. But with photons, this is more promising, as we shall discuss. So you can have a very large entangled state. So why not to change the complexity of the problem to design the circuit, to design the algorithm, to the complexity of generating the large number of qubits or photons in entangled state. If we make this trade-off, then we can find a promising direction of so-called cluster state quantum computer. Okay? A cluster state is a very large entangled state with different topologies, with different connectivities or entanglement. So every edge here represents entanglement. Okay? So GAC state is like a complete graph where everything is entangled with each other, n-qubit n. Okay? So it's like an information molecule or a cluster, large atom molecule with information focused on these links. Okay? And what we have learned in our today's lecture, this von Neumann measurement theory, there's a wave function collapse. I said this is bad, but here it's working on our advantage. If I measure part of this circuit, and the wave function will collapse somewhere, and I will make some changes on the circuit. Okay? But these changes, if I'm doing this on purpose, they can simulate a quantum gate-like operation. Okay? So by making some local measurements, I can effectively simulate a gate measurement. Okay? And I feed forward this measurement results throughout the circuit. Okay? It's like a Pac-Man eating some of the states and carving a path which simulates a real quantum gated circuit. Okay, so this is the basic idea of this or one-way quantum computing based upon a cluster state and local measurements. Okay? So they have different names, but actually its operation has all three of them. The other promising direction is, okay, this is a linear integrated photonic circuit, etc. But nonlinearity is not that bad, yeah? Why we don't like nonlinearity? Because it will create some coupling also to the outside world. So we will lose our pride that our photons are not interacting. They are so sacred and they are so noble. They will not care about the environment. But if nonlinearity is there, then I get the decoherence similar to superconducting qubits. But okay, if I can controllably introduce nonlinearity even at the single photon level without going to very high electric fields, maybe this is advantageous. And there is significant research going on to get a single photon level nonlinearity, like a cross-sky coupling and that kind of effects. And this is another promising direction for young people to look at. So how to generate this cluster state? The people consider some idea known as fusion. Because we have seen we can generate bad states relatively easily. We can generate 3 or 4 qubits even with superconducting qubits easily. But how to go higher and higher? So the idea is if we can generate 2 or 3 qubit entangled state, this is the graph of a 3 qubit entangled state, every edge indicates an entanglement. Okay. The fusion means let's get this molecule and fuse it with another one to make a larger molecule, larger information molecule. Okay. So basically, again, you can use linear optical elements. This is again directional coupler or similar to beam splitting, okay, and some photon detectors to realize, to sacrifice some entanglements. So you have here 6 qubits, but you only get entanglement between 4 qubits. Okay. So after you probabilistic generate these states, you fuse them, again probabilistic generate a 4 qubit entangled state. So from 3 to 4, the point is you cannot easily do this with superconducting qubits or other architectures. This is where the photons are coming in full winning state because there's lots of resources here and scaling to this and sacrificing these photons is already a very big problem in different architectures, but photons are abundant. We can easily get this with large number of photons. Okay, and also just talked about different elements and systems and defects to generate single photons, but also for the circuits there is a race about different materials. So currently the focus is on either silicon or lithium niobate. You can look at some references about them. And of course, we like silicon. We use it a lot in different applications. We have a lot of experience with it, and we have some bias maybe here. But these two are competing and popular materials to design our integrated photonic chips. You can look at also X8 chip of Xanadu and other works of Psi Quantum. It's getting less popular, maybe, but we will see. So there is also some promising, so this is actually an old idea, but getting more popular because of the possible developments in quantum computers or in the probable future. So again, this is revived a little bit that we have some secure cloud computing idea. Again, here the photons are more popular choice. And in the original paper also it was demonstrated using photonic system. Okay, so basically the idea is that in the cloud computing, it's better to use this photons for security, and all the parameters are inside the state so that you don't interrogate your system for parameters. Parameters are hidden and exhausted during the calculation. So here, this review, I also suggest that you can have a look at it. It is a nice, concise, short review of photonic quantum information. You can find maybe more recent one, but this has a lot of good information for a start. And just look at some experimental early work on the cluster computing. This is the leading paper, pioneering paper, with Walter and co-workers and Ziming and group here, Federal here, so some important people all together. There's a lot of good ideas also.